everybody, and welcome back to AP Psychology. As you know, this is where I will go over the content of each module of a particular unit. In this case, Unit 1, Module 6, which is Statistical Reasoning for the Scientific Method. So go ahead and pause for a moment, grab a pen, grab a seat. Don't forget to grab those notes in today's section of notes in your binder. Again, that's Unit 1, Module 6, Statistics. I'll see you on the other side. Alrighty, we are rolling right along here in our final set of notes for our Unit 1 Scientific Foundations for AP Psychology. This one is all about statistics. This one's a little bit heavy math-wise, but for those of you who don't feel that you're good at math, don't panic. We will, and I say it again, we will get through this together. Okay, I thought I would never be able to do math when I knew that I was taking on this course, and I even finally got it. So if you're like in an AP Stats course or even Algebra 2 trig class or calculus, you'll have a little bit of an advantage here. However, I'm really going to try to simplify this stuff for you, all of you, even if you don't like math or do well in math, and make sure that we're only really hitting on what you'll absolutely need to understand for the AP Psychology exam. Okay, so let's get to it. Our learning targets for today, as you can see, are pretty long again. I urge you to stop here or go back after today's video and read each one closely so that you can start getting more familiar exactly with what the AP College Board is going to be asking of you in terms of what you need to know for the entire year. Basically though, for today we are looking at how we apply basic statistical concepts such as measures of central tendency, variation, range, and standard deviation. We're also going to cover correlation coefficient, which was covered in research methods, and put it all together. We're also going to look at the distribution, that's like how the data is skews. Normal, bimodal, positive skew, negative skew. Bottom line is here, this is statistical reasoning, and what we have to understand about it is that it's all about the research, right? The statistics are everything about our research. So that after we perform our experiment, we can publish the research in a magazine or in a journal, and we can publish the outcome in ways that are measurable and understandable, and most importantly, replicable for other scientists. In other words, it's really about how we can use numbers to display what our research has found out. And so we have these statistical procedures that analyze and interpret data from our research, and they let us see what the unaided eye might miss. Okay, this slide is all about where you guys live, Queens, New York, right? For instance, we have some data here, which is from the Census Bureau. It's about the income for the county and state, which is Queens, New York, in which the population is over 2.4 million people who live there. The median household income is $72,000. There's also a 10.3 poverty rate, as well as a 60.2% employment rate. Notice I said employment, not unemployment rate. It means that about 60% of the population who lives in Queens and who are at least 16 years of age or the working age is employed. If you're interested in hearing more about census data and seeing what is reported by the Census Data Bureau, go ahead and look that up at uscensus.com. There's a lot of really cool stuff there. So describing data is really the first step that statistics takes for us. Meaningful description of data is so important in research, or just describing what it's saying to the person who's reading the data. And this is so important because misrepresentation can lead to incorrect conclusions. So let's take a look at the graphs that we have here. These two graphs are basically telling us the same exact thing. But if you look here at the first graph, it says that there's really no difference. But if you really zoom into it, you'll be like, wow, brand 1 trucks are so much better after 10 years of driving, right? Not so fast. If you take a quick look at this vertical axis over here, and you look real close, the second graph is showing the differences are between 85 and 100 percentile. Compared to the first graph, it shows the percentages are between 30 and 100%. It doesn't take a genius to figure out to see that how all 4 trucks are actually above the 95th percentile, and therefore there isn't really very much difference in their drivability after 10 years after all. It just goes to show you that there can definitely be some misleading information out there, especially when it comes to advertising. Measures of central tendency. So the measures of central tendency, and these are just probably going to be a refresher course for you, but it's the mean, median, and the mode. The mean being the mathematical average of whatever the scores are in the data set, which, by the way, you can always remember this one by saying to yourself, oh, that's the mean one. It makes us do all the math. Right? It makes me do all those arithmetic averages and dividing by 3 and To get the average in a distribution, you have to add up all the numbers in a data set and divide by that number, that total number of numbers in the data set. Right? That is just a fancy way of getting the average. The median is next up. Right? It's the middle score in a rank ordered distribution. Right? You can think of it because medium is a word that we use for something that isn't to anything, but it's just right there in the middle, right? It's medium strength, right? It's not very strong, it's not very weak, it's right in the middle. It's not very hot, it's not very cold, it's medium out. It's right in the middle. Whatever 2 words you want to put on the end, the median is in the middle. And third up is mode, which is the most frequently occurring score in a distribution. I usually try to remember mode because mode is spelled M-O-D-E and most is spelled M-O-S-T. Both begin with an M-O. So it makes sense that M-O-D-E is the number that is in the set that appears the most often. What are the ranges of the ages of people in your family? It could be as young as a newborn infant, or maybe you're the youngest one and you're 17, and it can go all the way up to your parents who maybe are in their 40s, and then maybe your grandparents who are in their 60s, and then maybe your great-grandparent even who's in their 90s. What we have next is what we call standard deviation. Deviation meaning difference, right? To be deviant means to be different from the norm, right? To be different from the standard deviation. The average difference between each score then. The average or the mean are the same thing. So what do I have depicted here are 2 distributions of scores. The red one, for instance, has a very small standard deviation because it also has a small range. The average distance or difference between each score and the average is really small. So you see, it's really tight in there. You could say that that's the standard deviation is around 10, whereas in the blue graph, you see it's flat and much wider, and therefore has a much wider standard deviation of 50 because there's a wider range of scores. So the tighter, right, the smaller the number, the more spread apart, the wider the range of scores. Okay, so let's talk a little bit more specifically about the standard deviation. Here's the good news. You will not, at least in this course, AP Psychology, you will not ever be asked to calculate the standard deviation. But you do need to apply what you know about the concept. So you have to understand it conceptually. For example, which of the following data sets has the greatest standard deviation? So go ahead and look at each one of these bullet points. Hopefully you're looking in between each of the number sets, right? This one up here is 1 to 30. So there's a difference of 4, then 3, and then a difference of like, I don't know, a lot, like 23, right? To get from 7 to 30, you have to go up 23 steps. And then the second one here, there's a difference of a 5, a 2, and another 5. This one on the bottom, there's a difference of a 2, and a 1. So that last one has the smallest difference. This one in the middle, probably the next smallest. But because of that big jump between the 7 and the 30, that top one really has the biggest standard deviation. see, you can really figure that out in most cases just by looking at it because of the spread or the range within the numbers in the number set. So again, how do you figure this out? Well, you can estimate the standard deviation by also not just looking at the spread or the range of the numbers visually. You can also find out the mean. You can also find out the standard deviation by finding the mean and then compare each number to the mean if you wanted to go the longer route. But who wants to sit there and add up and divide by those many things in order to measure each one when you can just look at it with your eyes, right? Okay. Normal distribution. A normal distribution is a distribution of scores that produces a bell-shaped symmetrical curve. As you can see on this chart here, in this normal bell curve, the median and the mode fall exactly at the same point, which is right here in the center. So you see that little zero there? That means it's a 0 standard deviation away from the mean. So I'll say it again. Here in the middle, the line that represents the mean, the median, and the mode. So what we're going to do here is talk about what you absolutely have to memorize in order to understand this. First, you need to know that each one of these jumps here, each one of these little jumps from each of these numbers from the 0 to the 1 with the little symbol to the 2 with the other little symbol, that means it is 1 standard deviation from the 0. The next one is 2 standard deviations. The next one here is 3 standard deviations away from the mean. The mean, the median, and the mode are all in the center, and you're always going up and down the normal curve. So what you have to memorize, what I recommend that you memorize, half of the curve, because anytime there's a normal distribution of scores, these percentages that you see here in the white and then in the black on the outside will always be in the same normal distribution of scores, and so on. The test, what they'll do, what they'll say on the test in a normally distributed amount of test scores, blah, 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 and then they'll give you more information. As soon as you see the words normal distribution of scores, you'll know that it's these percentages that you will have memorized already, right? These percentages between the normal deviation, 34.1, okay? For the next one, it's 13.6, and the next one is 2.1, and then the next one is 0.1%. But there's another percentage I want you to memorize from the mean line too. And all the way up is halfway up the curve, and that's 50%, okay? So those percentages are simply added together and make up half of the distribution, or 50%. I want you to memorize this because if you've got that memorized, it's easier to do the math. If you look at the left side of the standard deviation of the normal distribution, on the left-hand side, it's the same numbers. 34.1% is between 0 and -1. 34.1% is between -1 and -2, 2 steps away from 0, and 2.1 and 0.1, just like it is on the other side. Okay? I want you to memorize this because if you've got that memorized, it's easier to do the math. If we need to involve the other half of the curve, it's just as simple as the other half, except that it has negative numbers. Okay, let's move on to skewed data. All right, skewed data, skewed meaning off or set off or different from not normal, meaning it's not a normal distribution. It's not a bell curve. It means that the outliers that are involved in these data points that lie at one extreme of the curve or the other, and so they're different from the rest of the data set, right? They're skewing or changing the data. For example, let's say you gave a test, okay, and you have a normal distribution of test scores, right? Most of your kids are somewhere in the middle. Some of them got like 100 or a 90. Some of them got like a 5 or a 15. but most of them in the middle of the bell curve, right? Most are between 70 and 90. But let's just say Sally somehow got like 150%, which shouldn't be allowed, but let's just say that she did, right? That one giant score totally skews the data set, and now it's no longer going to be a normal distribution or a normal bell curve shape. So because of this, you have to know what both a negative and a positive skew is. You have to know whether the skew is positive or negative, which is determined by where the outlier lies. So in Sally's case, it's a positive number. But in a negative skew, which you see here on the left side, there's kind of a little dip on the tail. Let's just say that on what I call the negative side. It's not really negative, but it's on the lower end because we think of negative numbers as lower numbers, right? So the outlier, the extreme data point, is all the way down here on the low end. Whereas in a positive skew, like the right-hand side, the extreme data point is all the way on the higher end, or what I call the positive, because it's higher than the lower numbers. So which measure of central tendency is actually most impacted by the outliers? That's really an interesting question, right? So I want you to remember, on a normal distribution of scores, the mean, median, and mode all fall on the same line. So look at the skewed curves. The skewed data, which one goes the farthest away from what would be like the peak of the distribution? I'm hoping that you see it's the mean. The mean, or the average of a data set, is actually the most unreliable measure of central tendency. Why? Because it's the number most impacted by the outliers, right? Those people who score way off the charts or way under what they should have really impact that data set. Alrighty, so we're done talking about descriptive statistics. Now let's talk about inferential statistics. Now this involves estimating what is happening in a sample population for the purpose of making decisions about the population's characteristics. It's based on the probability theory. What it means is that you just get to infer, make an educated guess from your sample about your population. That's all it means. So basically, inferential statistics allows us to say, if it worked for this population or for this sample of people, we can estimate that it will work for the rest of the population. So for instance, let's take drug testing. If the medications worked for the sample of the people in the drug program, we would estimate that they will have the same effects for the general population. That's it. It allows them to generalize. We've heard about generalizing, remember? Of course, there's always a chance for error whenever we're looking at the findings. The hypothesis and the results must be tested for the significance. We can't just assume that because this guy did everything you're supposed to do in the research, that yep, it's true, we believe him, he must be telling the truth. He's a scientist. No. We have to use statistics to test it, to make sure that it actually happened, that it's actually true, meaning that it is significant. And that's with a null hypothesis. A null hypothesis states that there is no difference between the two sets of data, meaning it's like the opposite of your actual hypothesis. The purpose of the null is that until the research shows by proving the original hypothesis that there is a difference between your two variables, the researcher must assume that any difference present is due to chance until the end, when they know that they've proven it every time they've tested it. They have to assume that the difference is due to chance, or else there's bias involved. Okay? So let me give you an example of null hypothesis. Okay, one of the ways that we need to really do this is, and this is really before we even conduct the research in the first place, and that's with a null hypothesis. A null hypothesis states that there is no difference between the two sets of data, meaning it's like the opposite of your actual hypothesis. Like the y-axis, you could say over here, is the decision that the researcher makes, except the null, and then up top is the truth about what's going on about the population. That's that the null is either true or false. And then within there you have either a correct decision or a type 1 or a type 2 error. So with the type 1 error, wherein they reject the null, they choose the original, but the null turns out to be actually true. Uh-oh, big mistake. Then a type 2 error is where they accept the null, but the null is false. Another big mistake, right? So let's look at this in real world terms. Let's say the original hypothesis for a doctor has a patient who exhibits symptoms of appendicitis, meaning their appendix is about to explode, right? The patient comes in keeled over, pain in the back, pain in the front, can't walk, can't sit up straight. The appendix needs to be surgically removed, right? That's the original hypothesis. The medical doctor has to consider the null, though, without any surgery first, right? So the null would be appendicitis is not the reason, so let's back burner it, right? The symptoms are coming from something else. Therefore, the appendix does not need to be removed. They've got to consider both. So let's go through each one here. Let's say they accept the original, and it is appendicitis, but actually the null is true, meaning they go ahead and remove the appendix. But then the patient has unnecessary surgery because we find out later on that he swallowed a cup of screws and nuts and bolts, and that's why he had a stomach ache. This could result in malpractice, right? If you're supposed to do surgery on the stomach then and not the appendix, you're in big trouble, and the lawyers will come and sue for malpractice. Not good. If they accept the null and the null is true, they've made the correct decision, and unnecessary surgery is avoided. So they investigate other potential causes to figure out what's going on with the patient. Now they make another correct decision here. If the appendix is removed and the patient fully recovers, right, then they accept the original and the null is actually false. That's a good thing, right? And then the last one here is a type 2 error. They don't remove the appendix, but it is actually appendicitis, and the appendix explodes, and bam, he or she just risked the patient's life, and now they have to go into ICU. That's not good at all. Okay? I encourage you to re-listen to that part. Okay? Take the notes first time, and then go back and listen to it. It's a lot of common sense, but it's a lot. Okay, statistical significance. This is a really big term here, and we need to take a deep breath. We know that we can understand this because it really is so simple if you approach it that way. So stay with me, okay? All right, go get yourself in a good place, nice and comfy, and let's talk about this word, statistical significance. All right. The difference observed between your experimental control group of teachers who drink caffeine and teachers who don't drink caffeine is probably not due to chance, right? It's actually due to a real difference between the groups, which, if you've done your job as a researcher, you've controlled for all the other stuff that could be impacting their alertness or their happiness. So the independent variable, like we said, is caffeine, impacting the dependent variable of their alertness or happiness. If you can determine that through certificate statistical formulas and stuff that I'm not taking the mental space or time to understand, and nor do you have to for this course, then you know what statistical significance is. And it's just that it means the data is, quote, significant when the likelihood of the difference between your experimental, the one that got the caffeine, and your control group, being the one that didn't get the caffeine, is due to chance, is less than 5%. So when you have a difference between an alertness or happiness of your experimental control group, and it's less than 5% of it is due to chance. It's actually due to your independent variable, your caffeine. Then you have a statistically significant researcher data point. So in other words, there's a 95% likelihood that there is a difference due to your independent variable. The caffeine is the thing making the teachers alert and happy, right? That's where you want your numerical value to be in order to call it statistically significant. For this, we're calling it a p-value, and then it has to be less than or equal to 0.05 or 5%, meaning p, like chance, let's say out of only 5% or less of the difference is due to chance. Again, meaning that the rest, 95% or more, is due to the independent variable. This is important because if research is statistically significant, it means that the results are probably not a fluke or due to chance, that you actually have cause and effect, that you actually got something here. And if you don't actually have something, you're not going to publish it in all kinds of articles and magazines and medical journals and be known for all of your research, because it really means nothing at all, right guys? That's what we've got for statistics. Thanks so much for joining me on this wonderful journey of scientific foundations of AP Psychology. I hope that this has been helpful for you guys, and if it hasn't, please come to me on Wednesdays for remediation. Have a great day. I'll see you next week. Bye now.